Thank you, Valentin. So, my name is Mahesh Chandran, and I'm a PhD student at the Indian Institute of Technology, Bombay. The topic that I'll be discussing today is about how one can derive the equations of black hole thermodynamics from entanglement mechanics. It's based on a recent work of mine, which was published in collaboration with my supervisor, Shankar Narayanan. And before I begin, I would like to thank the organizers for giving me an opportunity to present at this workshop. Okay, so all right. So before I step into the motivation behind this talk, let me first recap some of the things that we already know about black holes. So when we consider a small infinitesimal change in the mass of the black hole, the resultant equation that we get is something that resembles the first law of thermodynamics. This is provided that there is a mapping between the mass of the black hole and its energy, surface gravity of the black hole and its temperature, area of the black hole and its entropy. In literature, there is also an integral form of this first law, which is known as the Coulomb relation, or equivalently the generalized Smart formula, which basically connects a conserved charge known as Coulomb energy with respect to time-like Killing vector if we are considering stationary spacetimes, and other quantities such as the Hawking temperature and Bekenstein-Hawking entropy. And in fact, you can rearrange this same equation in such a way that you can write down the mass of the black hole on the left-hand side and other quantities that describe the black hole on the right. And this is what is known as the Smart formula of black hole thermodynamics. And usually this equation is something that tells you something like an equation of state corresponding to the black hole horizon. What we also know is that there are quantum fluctuations of the horizon, which leads to Hawking radiation, and there is an entropy and temperature associated with this radiation. And you can see that the Bekenstein-Hawking entropy obeys an area law, scales as the area of the black hole horizon, and the Hawking temperature scales as surface gravity. And this is consistent with the mapping that is required to call this first law, to call this equation as the first law of black hole thermodynamics. But in this talk, what we are dealing with is what we want to address is what are the two microscopic degrees of freedom that gives rise to black hole entropy. So as you can see, there is a host of theories that can in principle derive black hole entropy and can explain its area law behavior, some of which are semi-classical treatments, some of which assume a fundamental structure of gravity. But essentially, there is a degeneracy when it comes to pinpointing which would be the true degrees of freedom that gives rise to black hole entropy. And this is what is known as the universality problem of black hole entropy. And entanglement entropy is the route we'll be choosing in this talk. And we'll be seeing whether we can address this problem using the entanglement approach. So the entanglement approach basically considers a semi-classical treatment wherein there is a quantum scalar field propagating in an arbitrary background spacetime, which is essentially classical. And as you can see, if you calculate the entanglement entropy for such a case, you will see that it also scales as the area of a separating horizon. And this is analogous to the Bekenstein-Hawking entropy. So this could be a possible way of explaining how black hole entropy comes about in the first place. But then again, you see that entanglement entropy is just merely a number, and it cannot essentially tell us much about the background spacetime, because this area law behavior that you see over here is a very generic result. You observe it in flat spacetimes, you observe it in black hole spacetime, so there is a limit to which how much entropy can tell you about the background spacetime. I'm referring to entanglement entropy specifically. So what we'll be looking at instead is the degrees of freedom that gives rise to this entanglement entropy. We'll see whether it can also capture other quantities related to black hole thermodynamics, basically Coulomb energy, Hawking temperature, and so on and so forth. And in this process, what we find out is that we can in principle present a new and independent derivation of Smart formula in black hole thermodynamics from the degrees of freedom that actually gives rise to entanglement entropy. And that will be the essence of the talk. And let us see how this happens. Okay, so we first consider a line element, which is basically static, spherically symmetric in 3+1 dimensions. The only difference being is that instead of radial coordinate, what we'll be looking at is the proper length coordinate. And of course, we are considering an FFR where we are considering a spacetime which has a horizon. Basically, the FFR has roots. And what we see is that this proper length coordinate is something which is 0 at the horizon, and calculates the distance into the region where FFR is positive. And this automatically rules out the degrees of freedom that are in the region FFR less than 0. Therefore, it's already a limitation in this picture that we're trying to use. But then we'll assume that we are only interested in the region where FFR is greater than 0, and assuming that, we will look at the action of the massless scalar field propagating in this space-time. And then we simplify the problem by first exploiting the spherical symmetry and using the partial wave expansion in order to reduce the problem that we have over here from a 3+1 dimensional system to an effective 1+1 dimensional system. The second thing that we'll be doing is lattice regularization. So here what we do is we'll replace the scalar field. We'll place the degrees of freedom of the scalar field at grid points in a lattice along the proper length coordinate system. So you can see that there is a lattice spacing associated with these grid points, which is captured in what is known as A, and A is basically the UV cutoff of the system. So now when you take the limit A going to 0, which is the continuum limit, you're supposed to get back the results of field theory as it is. Now, once we, at the end of this procedure, what we obtain is basically a Hamiltonian which looks seemingly complicated, but it's essentially a chain of harmonic oscillators that are coupled together. It is basically quadratic in phi lengths. So the next step of the process is to basically bipartite the system, basically bring a partition of the scalar field in such a way that it divides the scalar field into two, phi in and phi out. And we look at the correlations between phi in and phi out. And we will describe what is known as the entanglement mechanics, or what we mean by it, of this scalar field. So first of all, let us assume that the scalar field that is propagating is in a ground state psi 0. Now what we'll be doing is that we'll be tracing out the degrees of freedom corresponding to phi in over here. Now we do that from the density matrix. We have a total density matrix corresponding to a pure state, and then when we trace out the degrees of freedom corresponding to the degrees of freedom in phi in, we see that the reduced density matrix that we obtain does not correspond to any Hamiltonian. It's a mixed state basically, and the entropy corresponding to this reduced density matrix is what we understand to be the von Neumann entropy definition of entanglement. There are also other measures of entanglement, but we'll be focusing on this particular expression. And basically, we can also look at the total entropy of this system by adding the contributions of all the L and M modes. The second thing that we'll be looking at is the entanglement energy. So this was actually introduced first by Mukayama in '98, and it basically looked at the normal ordered Hamiltonian corresponding to the degrees of freedom within phi n and taking its expectation value. So you can also similarly look at the total entanglement energy of the system by summing over L and M modes as you saw previously. So what do these quantities essentially mean? These are quantities that are defined with respect to the an artificial boundary that you bring into the system. So if you entanglement entropy measures like the net change in information content when you bring in this horizon, whereas entanglement energy is supposed to capture the net change in the vacuum energy of the system. And this provides the foundation of what we understand, or what we call to be entanglement mechanics. Now, what we will be looking at, what we are interested in doing, is looking at the properties of these degrees of freedom when it is very close to the horizon. In order to do that, you have to bring this boundary very close to the point rho equal to 0, where the horizon is lying. So basically, what we'll be doing is that we'll be tracing out the first oscillator very close to the horizon, and that should, in principle, at least approximately capture the results corresponding to the black hole horizon. Now, let us look at the results, how it turns out to be. So we'll start with the simple case of a Schwarzschild black hole, where we have an FFR which has this form, 1 minus 2 by r, which is very familiar to all of us. As it turns out, the entanglement entropy follows an area law, which is expected, but entanglement energy follows a linear relation with mass. And we see that the ratio of E by 2s gives us a quantity which is proportional to Hawking temperature. Now, if we add more complexity to the situation, we can add a charge, and we can consider Rice-Nordstrom black hole, which now has two horizons. Here, in this slide, I have presented the results for the outer horizon, the event horizon of the Rice-Nordstrom. And what we see here is that entanglement entropy follows an area law, no surprise there. But entanglement energy, on the other hand, has a scaling relation which is equal to root of m squared minus q squared. And now if we take the ratio of E plus by E to S plus at the horizon of the horizon Nordstrom, we see that again it is proportional to the Hawking temperature of the event horizon. Now we look at a slightly different case. We consider a Schwarzschild black hole, which is now in a static patch of a de Sitter spacetime. And we see that here again there are two horizons. One is an event horizon that is inside, and then there is a cosmological horizon which is on the outside. And instead of looking at the event horizon as we did in the previous two cases, I have presented the results here for the cosmological horizon. And we see that the entanglement entropy follows an area law. Entanglement energy follows a scaling relation as RC minus 3m, where RC is where the cosmological horizon is. And then when we calculate E by 2s, we see that this is again proportional to Hawking temperature. So we consider these simulations. We run these simulations for a host of spacetimes. Start with Schwarzschild, de Sitter, RMBH, Schwarzschild ADS, Schwarzschild DS, and we also consider each of those horizons as well. In some of these cases, there are two horizons, so we consider each of them separately as well. And in all such cases, what we observe is that the proportionality constants that I showed, CE and CS, they are exactly the same. It is universal for all the spacetimes that we considered. Then we observe that there is a one-to-one correspondence between quantities of entanglement mechanics, which is E and S, and quantities that are associated with black hole thermodynamics, which is Komar energy in black hole Wittgenstein-Hawking entropy. But then, apart from that, we also see that there is these quantities associated with entanglement mechanics are related to each other in a way that is very similar to the Komar relation, where E is equal to 2 times TH of S, TH into S. Now, if we use the one-to-one correspondence equations over here and substitute back into here, we'll get exactly the Komar relation, because all these proportionality constants are such that they cancel out. And this is something independent, as you notice, it is independent of A that pops up over here, which is a parameter that you essentially have to tune. It depends on the model that you're looking at, how big the UV cutoff is or how small the UV cutoff is. But irrespective of what that parameter of A is, we essentially get the Komar relation from the entanglement mechanics regardless. So this is a summary of the results that we have obtained for all these spacetimes. We obtained an entanglement mechanics structure as follows, and then from there we were able to obtain a thermodynamic structure, which could just be rearranged to obtain a smart formula corresponding to that spacetime. So if you're looking at a spacetime for which you don't know any of these properties thermodynamically, you can still use these simulations to figure out what the smart formula would look like in those cases.
Sorry, you have a couple of minutes left.
Yeah, I'm essentially done. Okay, so in order to conclude or to sum up what I have presented here, what we observe is that there is a one-to-one correspondence, again, between quantities associated with entanglement mechanics and black hole thermodynamics. And we see that Komar relation and smart formula associated with black hole thermodynamics are exactly recovered, which is basically an independent derivation of the integral form of the first law of black hole thermodynamics from the degrees of freedom that gives rise to entanglement. And we have also considered static spacetimes over here, but somehow the entanglement mechanics of scalar field phi captures the dynamical properties of the background spacetime. And if you're looking at where we're going forward with this, we can look at situations which are much more general. We can look at curved black holes, which is more complicated, and modify theories in higher dimensions, and if all these relations and interrelations between entangled mechanical quantities, whether they hold. Another thing that we are currently looking at right now is the entanglement mechanics in a time-dependent background, which is pretty involved, which gets pretty involved, but we're hoping to publish some things in time soon. So yeah, that'll be all. Thank you very much for listening to me. If there are any questions.
Thank you very much, Mahesh. So are there any questions? Please raise your hands or type them out in chat. I see there's one question in chat. It says, thanks for the talk. Do the results depend on the lattice regularization that you choose? For instance, the universal constant that you found?
Yeah, so let me answer that. So it does not. The proportionality constants do not depend on CA and CS. There is a reason for this. Let me just go back to. Yeah, all right. So if you see here, you can see that the HLM that I've defined over here, there is a 1 by A sitting outside. So in system in Hamiltonians that are quadratic that are essentially quadratic, we observe that there is a scaling symmetry of entanglement entropy. Basically, what it means is that if I have an edge and if I rescale it by a constant, we still get the same entanglement entropy in both cases. However, the energy gets rescaled, but this rescaling of the energy is in such a way that when you look at when you go back from the rescale system h by a, for instance, to the original system h, which deals with the scalar field, this a square actually cancels out. So the proportionality constant that we obtain is actually CS and CE, but A square is something, if you're looking individually at entanglement entropy and entanglement energy, it is still there. But if you look at the ratio, the A square just cancels out. So while this connection, in this connection, this A square factors in, the relation between E and S will not have a dependence on E square. And therefore you can derive Kumar relation regardless of the lattice regularization that you choose.
There's a follow-up to the question. It says, this is a spherically symmetric lattice, right? What happens if you change to a non-spherically symmetric one?
Well, for starters, it gets messy, but we have tried looking at curved black holes, and there are very specific cases where you can, for instance, when you look at it perturbatively, there are ways in which you can obtain an entanglement entropy, but it's still very limited. So it is something that we're still trying to figure out. So that's something we'll be looking at. It gets especially complicated because you cannot reduce the system from a 3+1 dimensional system to an effective 1+1 dimensional system. So yeah, that's why it is quite difficult to obtain entanglement entropy. Thanks.
Okay.